Okay, welcome back, guys. So this is going to be the third YouTube video already, and this is actually already the last part of chapter one. So we are going to complete it today. So yeah, and after this we will go to some 2021 trials and 2022 trials based on your feedback, and also we can see what kind of patterns of questions that will be generally asked from this chapter based on the analysis from all these trials. Okay, so first of all, today's topic is going to be inverse functions, as you see here. So how are we going to understand inverse functions better? Is look at this concept over here. So the concept of inverse function actually comes from what we did earlier, which was the composite function. So you can see here, these are composite functions here, g, f, and fg. But I added an inverse function here, which is g inverse and f inverse, to cancel out one of the functions that make up the composite function. So why I do that is so that I can find the thing I wanted to find here, which is fx and gx. And why I can do this is because of this indices law we have learned that a power 1 times a power negative 1, you will get a power 0, because 1 plus negative 1, you get 0, which is 1. So you will get back the original function, which is g or f, to get gx and fx respectively. Okay, so this is something just like starting to the uh, inverse functions. So this is an example of question I put. So I'm going to show you two ways to solve. One way is the typical way we learned in our last video, which was using composite function normal method. And now what we're going to do is something related to our lesson today, which is the steps how to do an inverse function. So let's say I give you fx is 2x minus 5 and gfx is 8x minus 24. So you must know what is happening already from this kind of pattern of functions, which is the object, which is the image. So all of that you can find in the last two videos that I did. So now the question comes, find gx. So let's say I want to start with the normal method first, method 1. So they already gave you gfx here, 8x minus 24. So what we can do is we express the left hand side of the equation, this part, which is gfx. So we are going to make g bracket the fx function. So what's the fx function? You can see it over here as 2x minus 5. So g bracket 2x minus 5 is 8x minus 24. So what's the step we do here, like in the last video, is we will let y equals 2x minus 5. So that we can find g bracket y. So after that, we will look at this part, which is we have to express the equation x in terms of y, because we want to find gx. That's the ultimate goal here. So how we can do that is by finding x in terms of y, so that we can substitute the y variable into the x part over here in 8x minus 24. So you will get here gy, because we already made the assumption here y is 2x minus 5. So after you solve, you will get gy is 4y minus 4. But then they ask gx, so we're going to sub y with x, like the normal method we did in the last video. So you should get 4x minus 4. So you just change your object from y to x, and it'll map to the same image, which is gx now. Previously it was gy, because we followed the pattern of the object and image. So basically what we did here was actually the inverse function already. Now I'm going to introduce on this side. We'll see the similarity here and here. It's just that these two variables will interchange. So the method that we applied earlier in the composite function is actually related to what we're going to see today, which is the inverse function. So if you look at the second method here, you want to find the same thing. You want to find gx now as well. So you see what I'm doing here is I'm applying the inverse function f inverse x to the f here. So that f power 1 times f power negative 1, you will get 1 back, means f power 0. So you will get gx. So that's our goal now. So what we can do is, first of all, we need to find f inverse x because we cannot work anything out with fx, and we don't have gx also. We only have the composite of gfx here. So we are going to make an assumption, let f inverse x equals y. So later on, I will show you why I can show this assumption. Basically, I can show here. Let's say this is x, this is y. So f will map x to y. So this is the normal thing we learned earlier, fx equals to y. Or you can say y equals fx. Quite common because fx is an image and y also is an image. So if I go the other way around, this is going to become f inverse because we are switching the journey. This f function maps x, which is the object, to y, which is the image. But now f inverse is mapping y, which was initially the image, back to the object x. So we are switching the journey now. So if I read this function f inverse, it will come f inverse y is x. So this should come the object now, which was initially the image. So this is why I made the assumption here, f inverse x equals y. You can also read it this way actually, because the numbers are the same. It's just where you want to map to what. So just because we want to use y as an image, we will put x as the object, not to confuse things here. Because f inverse y as an object doesn't look quite normal. Like usually we have y as an image. That's why we put y as on the right hand side of the equation. So after this next step, I put x equals fy. So why I do that is because I want to get rid of this f inverse 1. So what I do is I shift this to the other side of the equation. So when you shift something which is inverse, means it's something like 1 over f. You shift it to the other side, you're going to get f, because you'll divide 1 over f, means times f. So that's why you get back f here. So it's fy. So then you will express. So you're going to substitute your y as the object into x here. So you will get x equals 2y minus 5 instead of 2x minus 5. So you just follow the changing object to suit the equation. So now our goal is to find y, because if you find y, we will already know what is f inverse x here, because we made the assumption here, let f inverse x equals y. So after you do your algebra, you will get y is x plus 5 over 2. So f inverse x, we can conclude that is x plus 5 over 2 as well. So what it's actually trying to show here is the inverse function. This is also actually y on top here, as you can see. So the function that goes from here to here is x plus 5 over 2, in other words. So that's how I represent it with an arrow diagram. And yeah, so after I get this thing, we can already apply the concept, which is this one, to find the gx. So how to find the gx is we will do gf f inverse x. So you will substitute the f inverse inside the gfx function, which is x plus 5 over 2. So it's up here. And then this will in turn become your object. So when this becomes your object, so after when it becomes your object, you can substitute it inside here, because this is the function now gf. So it will be 8x plus 5 over 2 minus 24. So you solve, you will see that you will also get the same answer here. And if you notice this part and this part, it's also the same, which is applying the composite, the inverse function methods, almost the same. You can see here the final answer I get x equals y plus 5 over 2. Here is y equals x plus 5 over 2. Only the variables are switched, but the constants are still the same. And the way it is written, like a variable plus a number over 2, a variable plus a number over 2. So you can see there's a similarity between these two methods. So yeah, that's just to bring in the concept of inverse function, basically. So now we will go through the proper inverse function. Okay, so first of all, inverse function, we are doing now subtopic 1.3 already. So before I enter inverse function, let's understand a bit about the word inverse. So what can you think as the word inverse is something like terbalik lah, like different from the original function. So what I can see from the word inverse is three things. So I'm going to recall some of the lower modern math chapters that have this word appearing so that you know what inverse actually means in the context of math equations. So I've chosen a few chapters, a few subtopics in chapters that might help. So you can understand what is the process that's happening behind this inverse function thing. So first of all, we are going to logical reasoning, inverse variation, and inversely proportional relationship. So first, let's talk about logical reasoning. So if we see logical reasoning, right, if you can recall your Form 4 Modern Maths Chapter 3, you will realize that, let's say I give you an implication. If P then Q, let's say I give general variables to represent the sentence. So when you do inverse, right, the format is if negate P, then negate Q. So you see there's a negation happening here. So you can see the relationship between an inverse function with an implication. Let's say I call it a normal function. You can see that both of them are opposite to each other. Means one is yes, one is no. So that's why you see from a normal equation like this, your inverse function might be, let's say, like this. Means from without having a fraction to a function that is having a fraction. So you can see there's a difference in terms of the equation there. So yeah, so this is the general part for logical reasoning. And another topic that's more closely linked to this is your inverse variations or the inversely proportional relationship. These two are almost the same. So how you understand this is through this kind of graph. So normally you have y against x graph. So let's say here y is directly proportional to x, you get a straight graph, right? But then if you get y is inversely proportional to x, your graph will come like this shape. So this is something that is related to the inverse function. Not all inverse function graphs come like this. They depend on the equation you get. If like this is a linear equation, so you still get a straight graph. But let's say the function given is a cubic function, let's say, and you do an inverse, the shape might come maybe something like this. We don't know. You have to plot the values and find out how the shape comes. But one thing for sure is the main thing that can show the relationship between a normal function graph and an inverse function is it will always reflect on this line y equals to x. And this line, we know that any point on the graph, it will project to the same coordinate. Let's say here is 2, here is also 2. Means this point is 2, 2. So this is why we call it the point of reflection. So this is an axis of symmetry, we can call. So we'll go into that later on this. So yeah, this is kind of the briefing you can expect from inverse functions. And another thing inverse functions tell you is, let's say y is inversely proportional to x, you get y is k over x. So this I'm converting variation to equation form. So function is something like an equation. So when you shift x, right, you'll realize kx is power -1. And inverse function has a notation like this. So you can see the similarity here. F inverse 1 and also x power -1. So both have already undergone the inversion process. So that's why we call it inverse variation. And also this is also inverse function. So you can see inverse function always applies this power of -1. Means it's like reciprocal. So yeah, this is the concept here. So now we can go to a situation involving inverse function. Okay. So example of inverse function. So in this example, I'm taking different units of temperature. So what are the different units of temperature we have? We have Fahrenheit, we have Celsius, we have Kelvin. So the most common one used today is these two, of course, not Fahrenheit and degree Celsius, although Kelvin is the SI unit. So we are going to focus our eyes on these two only, because the conversion can involve an inverse function. These two is just a relationship of +273 degrees Celsius. There is also an inverse function here, but it's not involving any fractions or something like that. So you can see the relationship clearly to here. Because most of the questions in inverse function, the normal function will be a linear equation and the inverse function will come out to a fraction in most equations. So this is a good example. So it is given that Fc is equal to 9/5c plus 32. So what can you understand from here? So from here, we are actually trying to convert degree Celsius to Fahrenheit. Because you can see here, C is the object, because it's expressed in the equation on the right-hand side. And Fc, which is Fahrenheit, is the image. So if I draw an arrow diagram, it will look like this. C will be here, F will be here, and the function mapping it is Fc. And is equal to 9/5c plus 32. So whatever C value you have here, it can map. Let's say I put 5. Let's say the temperature is 5 degrees Celsius. So you want to know it in Fahrenheit, you just sub C is 5 here. You will know that Fc is equal to 9/5 times 5 plus 32, which is 41. So this is an arrow diagram to show the relationship between these functions. And in this case, you notice that F is the subject of formula, or we call it as the image. So this is something like express F in terms of C. So how if I want to express C in terms of F? Let's say I want to go this way. Express C in terms of F. So how can I do this? You can say that shift the equation to make sure it comes to this form. That's one way. But what's the concept behind that is we are actually applying inverse function. The process of shifting the equation and variables to get into this format is known as the inverse function process. So let's see how we are going to shift it together. So I'll do a bit of calculation. Let me on this first. So we are basing on this relationship here to continue our inverse function. Because this is the fact, this is based on experimental data. They construct this kind of formula to count or convert quantities involving Fahrenheit and Celsius. So we're going to start with that equation. Okay, so we have Fc is 9 over pi c plus 32. So now I want to find out what is the temperature in degrees Celsius if Fahrenheit is given. Just now was opposite. So we can do a bit of shifting here. So let's say I put 9 over pi c plus 32 is F. I just take out the c to make sure the calculation becomes more simple only. So when I shift, right, I can bring the integer to the other side. So you'll get F minus 32. And C will become F minus 32. So you see you're bringing a fraction over. Whenever you bring a fraction over, you will inverse the fraction. So that is where the inverse function takes place. So can you see from a normal linear equation like this is something like the linear equation because you can compare the relationship like this. Let's say Fahrenheit is your y-axis and Celsius your x-axis. You see it satisfies the condition of a linear equation. But look at this. This is in terms of we already factorize it to come as a fraction, pi over 9. Means when we expand it inside, you will get something like C equals pi f minus 160 over 9. So can you see how it's converted to a fraction form from this form? So that's why we already applied the inverse function process here. So that's how we inverse, how we want to find a separate quantity from the given quantity. So let's say, so how we're going to express this now is we will write CF is pi f, no need, we take the original one, pi over 9 f minus 32. So now you see, f becomes your object, but Celsius becomes your image. So if the arrow diagram comes out again, Fahrenheit will come here on the left hand side because left hand side is always object, but Celsius will come here, which is your image. So if I want to draw a function, this will be CF equals pi over 9 f minus 32. So let's say I put a value here. Let's say I put when Fahrenheit is, let's see a number that can divide easily. Let's say I put 52 Fahrenheit. So you will find out that your Celsius will get 100 over 9. So you can find out the value to your calculator, of course. So that's how we can also prove that negative temperature exists, because not always your Fahrenheit value is going to be more than 32. If it's less than 32, let's say I want to put 18, let's say. You can see here 18 minus 32, you already get a negative 14 here. So that's how we can prove that negative temperature also exists through this formula. So as I Celsius, you can find negative value in colder countries. So that's how we find the inverse function here from the original equation. This is your RV. So that's how we convert it using inverse function. So yeah, so this is how we do the inverse function process. So almost same concept like just now, but this one is about daily life. We're not using X and Y anymore. We're using between units. So now we'll go back to the normal one, which is frequently asked, which is X and Y, of course. Okay, so a few important things to note. So first of all, when we do inverse function, we have something like this, right? This is not the meaning. I can tell an example. Let's say fx is 2x minus 3. Your inverse function will not get this 1 over 2x minus 3. It's not just by doing 1 over. There's much more to it. That's why we have to shift variables here and there. It's expressing the equation x in terms of y so that we can find back the f inverse x. So it's not just by doing 1 over the equation given the question. So that's one common misconception. So you have to know that this f power negative 1, the negative 1 is actually showing inverse of x, inverse of f, and not reciprocal. So this is an important thing here. Reciprocal means 1 over something, let's say x. So it's not showing this part here. So it's just showing you an inverse function only. So yeah. So now we will go to the proper part of inverse function. So again, I'm using this arrow diagram because it's a good way to show you the inverse function. So let's say I got y and z. So y is your object, z is your image. So how we're going to do the inverse function is, let's say function f maps y to z. So how I write it is, fy is equal to z. And you will know that inverse function will always go in the opposite direction, which is here. So if I follow the arrow here, I will get f inverse z is y. So how do I know whether I wrote this is correct? As I said before, we can shift the f to this side of the equation to make it f power 1. So you see you get z equals fy. And you can see these two are equal. Fy is z, z is fy. So it's proven. If I do f minus 1, y is z, you will get y is fz, which we haven't found in any point here. So that's why we can know this is a wrong relationship. Means you have to inverse the object here to get the image back here. So that's what the inverse function is telling you here. So yeah. And also I told earlier the inverse function is always symmetrical at y equals x. So it's from here to here, something like that. This is y equals x. Let's say I use the board as the axis, y-axis and x-axis. So if I have a function like, let's say like this. So if your inverse function, you're going to reflect it here, you should get something like this. So you see the coordinates will always be equal. It means this length and this length will always be equal. Of course, here it's not drawn according to scale up, but the distance between the inverse function and the normal function will always follow this line here, y equals x. So this is the concept. So next is through arrow diagram. You can show also inverse function. Okay, so arrow diagram, let's say I have x and y here. Now I go back to x and y. Okay, so let's say g is the function that is mapping x to y. And I have values like 0 and 8 here, and negative 6 and 2 here. So let's say I say 0 maps to negative 6, and 8 maps to negative 2. So you have to follow the arrows here to see which is the object and the image. So I can say function g maps x to y. So let's say I give you the function gx is x minus 6. So you can see clearly here, because you see the pattern is 0 to 6. 0 to negative 6 is you minus 6, and 8 to 2 is you minus 6. So there's a pattern happening here. So now let's say I throw to you a question. Determine, the first one is g inverse negative 6. So you can use two ways here also actually. First, you can just say by referring to arrow diagram. G inverse negative 6 is 0. Means you just cross back the same journey but in the opposite direction as I showed just now. Means your negative 6 here actually is your y and you will get your x here. So this can also become your x and y depending on your arrows. So when if the right hand side becomes x and the left hand side becomes y, it's because of this inverse function. It changes the direction. So not always left is object, y is image. This is under a normal function g. But this way is g inverse. Means here comes your object, here comes your image. The arrow always shows which is the object and image. So that's why this now comes your x and this will come your y. So g negative 1x, g negative 1 negative 6 is y. So you can see from the general formula, g inverse x is y, and that's what I said just now, f inverse x is y. So you can see the pattern happening here. So under different functions, you can actually map your object, which now comes here, to your image, which comes here now. So this proves that this concept here is correct. So yeah, we are inversing the object to get back the image. So let's say I want to find what is the x value can get the y value. So now we know the x value is negative 6. So I can directly conclude from here, or I can find the inverse function of this and then substitute the x value. So you can try out x will come gy from here because I shift the g to the other side to be positive. So x will be y minus 6. Y minus 6 is x. Y is x plus 6. So I can conclude that g inverse x is x plus 6. And when you substitute x is negative 6. Because now here becomes your x when you're doing inverse function. Always follow the arrow. So you will get g inverse negative 6 equals, you can substitute your x here with negative 6 also. So it's negative 6 plus 6 equals 0. You see? I've proven this to this inverse function that direct loop also you get 0. You apply the mathematical way, you also get 0. So it proves that this inverse function relationship is correct. So that's how you test it to inverse function. So yeah. So in G inverse 2, it also applies the same thing. You do the same thing here, you will get this equation. You sub 2 into x, 2 plus 6, you get 8. Then 8 also. So this is the correct function or inverse function. So yeah, that's the thing here. So let's say I want to I'll summarize the steps here first. Okay, so the first step we do is always when doing inverse function is we let g inverse x equals to y. So this is the step I did just now. So as a summary, we revise these steps. So x equals to gy because we shift the g to the other side. And based on the just now question, I get x is y minus 6. So this is why I sub x with y here is because my function is using y as an object and no more x as an object. So that's the step here. And then the second step we're going to use is we want to find y in terms of x to satisfy this condition on top here. So you shift, you will get y is x plus 6. So you can conclude that g inverse x is x plus 6. And then you can use this equation to solve any question they give you in two sections. Let's say they got part A, find g inverse x when x is 2. So you can directly know the value from this equation. if they didn't give you the arrow diagram, this will come in handy because you have nothing to refer to. You have to apply the inverse function. So let's say I want to go opposite. Is it possible or not? So let's say I have this inverse function. I want to find back the gx function, which was originally x minus 6. So we're just going to reverse all these steps to find back. They can ask you also find back the gx function. And then they have to give you an inverse function, not then only you can start. So they give you g inverse x is x plus 6. So what they're going to do is, you just have to write this all back, but in an opposite manner. We already know that g inverse x is y. So you can say that x plus 6 is y. So now it's y in terms of x. So why not I express x in terms of y, which was originally the question. So I will get x is y minus 6. And we know that from here, if I shift here, I get x is gy. So I can put the gy inside here. Gy is y minus 6. And if I replace y with x, I will get gx is x minus 6. Same way. You see, it's proven. I can do it in an opposite manner also. When I go from normal to inverse, I can also go from inverse to normal. So our mind should always work in two ways. You have to able to do the reverse thinking method also, not only follow one way, which is from the normal to inverse. We can also do from the inverse to the normal. So this is what the question can sometimes ask you. So here I've got one interesting question. And this question is to show why a quadratic equation cannot have an inverse function. So it's coming to a very important part of this inverse function. So let's say I have a function f(x) is x squared over x minus 3. Anything with power 2, you can already expect is going to have a quadratic form already. So when they have like this, you have to put a condition x cannot be 3. Because the denominator, if you have 3, you're going to get back 0 already, which is infinity. So let's say I want to find this part. So this is how I prove that quadratic function will not have an inverse function. So let's say the question is like this. Find object of 8 under f. This is a normal kind of question, only no inverse here yet, because we cannot do the inverse actually through this method. So let's say they say object of 8 means 8 is your image, right? So you can say let fx is 8. And you will get 8 equals x squared over x minus 3. And then you try to form the general equation. You shift this to the other side. And then you shift it all to the left-hand side. You'll get this. And you realize you cannot factorize with your calculator. You can see here. My A is 1, B is negative 8, C is 24. You see you get these same values of 4 and 4. And you can see the arrow shows up and down. Means these roots are not real actually. No real roots. And how I prove this is a concept we learn in the next chapter, but I'll show it now. Is to the discriminant. So I'm going to use this formula b squared minus 4ac to show you that this equation has no real roots. So when you find out your discriminant value, you will get 64 minus 96, which is negative 32. So you know negative 32 is less than 0, and the knowledge from that chapter tells you that if your discriminant is less than 0, means your function has no real roots. So that's why I'm telling you that quadratic function is quite tough to get an inverse function, because you will never touch the x-axis over here. You will be hanging somewhere on top here like this. And how are you going to reflect this on the line y equals to x when you don't have a coordinate that is linking between the x-axis and y-axis, or somewhere close to it at least. So that is why it brings the concept that two objects have one similar image. Because in quadratic, we always expect to get two x values usually. So these x values actually represent the object, and they link to one similar image because we say let the whole equation equals to 0. 0 is your similar image. So whenever you have two objects linked to one similar image, if you can recall, it is many to one relation. Many to one relation is a function because it ends with 1, but doesn't mean it has an inverse function, because if there's two objects, I can prove through a test. Where should I do it? Let's say here, I do on top here. Okay, let's say the function, let's say I give you a random quadratic function like this. So, okay, we're going to apply a test called the horizontal line test to see whether it has an inverse function or not. So you can see if I draw a horizontal line here, it intersects at 2 points of quadratic function. Means I can conclude that there are two objects here, let's say x1 and x2, which have the same image here, let's say y1. So this shows the many to one relation, which shows that it cannot have an inverse function. Only if it cuts to 1 point, it can have an inverse function. So let's say I have a linear equation. Okay, so wait, so before that, let's try to differentiate between vertical line test and horizontal line test. So you can see the significance and difference between these two. So we learned vertical line test earlier already, and now they introduce a horizontal line test. So vertical line is to see whether it's a function or not. And here is to see whether it has an inverse function. Okay, so vertical line test says that, let's say I have a graph of, let's say this is x, this is y, this is 0. Let's say I have a cubic graph. So this is something like the shape of a cubic graph. And also I draw another cubic graph here to show vertical line test and horizontal line test. So vertical line test, see I draw like this on a cubic graph. You can see that only 1 point, means it is a function, of course. In fact, all graphs, if you try a vertical line, you will only get 1 point. See here, I get 1 point. Here, if I intersect, I get 1 point. Here, I intersect, I get 1 point. So you can see that every function is showing a one-to-one relation by this vertical line test. But then if I try a quadratic on a horizontal line, right, you see you already get 2 points. So this actually shows a deeper picture to the inverse function, that the inverse function cannot exist. But it is a function, but it does not have inverse function. So not all functions will have the inverse function. That's the relationship here. Not all functions have inverse function. Let's say I want to find out whether cubic function has an inverse function or not. I try horizontal line. See, 1 point only. Means one object reflects or projects to one image on the y-axis. So it means this has an inverse function. It has. Let's say I want to try linear. Linear also horizontal line test, so it has inverse function. Only quadratic. So I can conclude this one here. Not all functions have inverse based on the shape itself. So this is the difference between vertical line and horizontal line. Because function we have to fulfill image with only one image. That's why we see the vertical line. But here we want to see object only one. So these two contrasting things we want to see to this test. Because vertical line test, we can already see how many coordinates it intersects on the vertical line over here. If we intersect only one, means there's only one image. But then here, if we try horizontal line, we can find out whether the object has one or two based on this quadratic function example. You can see there's two objects when we try. So vertical line test is always to differentiate many or one images, but horizontal line test is to differentiate whether it has only many or one objects. So that's the opposite part between these two functions. So the easy way to remember is to, by just trying it out on random graphs, you can see the relationship already. So yeah, this is the example. So next part of this, we are going to see a few conditions about normal functions and inverse functions. So let's say I give you a condition. If f and g functions are inverse to each other, so they have to apply a few conditions here. So first of all, the domain of f means domain of f function is the range of g function. So you can see the opposite here. One function that has the same value on another function. Domain means your object or x-axis as we learned earlier in 1.1. And range is your image or your y-axis. So you see the same objects on a function can have the same image on another function. So that's the relationship between normal functions and inverse functions. So another condition, so the graph of G is the reflection of F under line y equals x. So this can apply both ways also. That depends which one is your normal function, which is your inverse function. So you can you can draw the normal function from an inverse function. Let's say I give you an example here, x and y. Let's say I have an inverse function at this coordinate of 0, 2, and the graph goes like this. So how are you going to find your normal function from this? So you must draw this imaginary axis of y is x, and you'll notice that, I have to be precise here. So let's say this is your 2, 0 here. So your graph will look like this. So you can see it's not accurate, but you can see something like a reflection. The distances should be equal with each other. So you can see the pattern like opens up like a mouth like that. So you have to follow it. This bends like this will bend like this. This is your fx. This is your f inverse x. Can you see? Same coordinate. So it applies this one. See, domain of f function is the range of g function. See, this is the same value. 2 is your object or domain, but here is your range or the image on another function. So you see, it satisfies this condition. And this condition also same, not it's a reflection on the y equals x. So the coordinates are always inverse to each other. So yeah. So this is the thing here. And let's say you're struggling to grasp the concept of inverse function. There's another method to understand as well. Try to recall your inverse matrix. So this one also applies the concept of inverse. So let's say I give you two matrix like this and equals to this kind of matrix. So this one we call it as the identity matrix. So what I mean by inverse is, let's say this is A, this is B, and their multiplication is equal to I, which is the identity matrix on top here. So let's say I give you random numbers here. So how you do inverse matrix is you will switch the numbers here and add negative to the numbers here. And when you times all these two matrices which I don't show now, you should get this. So you can see that this, how to do inverse of this is you still apply 1 over AD minus BC, then you have something like DA negative B negative C. So you can see this applies the concept of inverse, like F negative 1. So this is a good example also to show you what is actually inverse function happening here. So yeah. So in a general form, let's say I have point AB lies on graph F. So I can predict that point BA will lie on a separate graph. Let's say I call it graph G. If these two graphs are inverse to each other. So you see, I can make a conclusion of the coordinate, a random coordinate on the graph, because they are inverse function. So that's another thing as well. So another way that can show you the inverse function is you look at the arrow diagram. So you have four relations, two of which are functions, which is one-to-one and many-to-one relation, but only one-to-one relation can be called as an inverse function, can have an inverse function. So let's say we take out these two relations and study them. Let's say I give you random numbers. 4, 8, 6, 9, 36. Okay. So let's say I map like this. This is one-to-one. And let's say I just map like this. I put another number here. So can you see here it's converging to 1 point, means it's many to 1. Many objects, 3 and 6 have one image, which is 9. And here is 1 to 1. So this will have an inverse function. And I can show you why. Because let's say I want to find inverse function of 4, you will get 2. Because I can just draw an arrow back like this and say like this. But look at here, it's more complicated. Why I say there's no inverse function. Let's say I want to do an inverse function of 9. I go back, I can have two objects back, 3 or 6. So which one I want to choose? So we can't just choose anything we like. So that's why they say there's no inverse function. It means we don't have a definite number on the left-hand side of the object. Compared to this, let's say I want to do inverse 4, I just get 2. I know the answer this. So this is how the arrow diagram can prove you that many-to-one relation it's tough to find an inverse function because there are more possibilities than one. So yeah, that's one of the ways. So we're almost coming to the end already, to application questions already. So another way to prove so although this chapter 1 might not have many proving questions, this one is quite a good proving question actually. They can ask you to are these two functions inverse to each other or not? Let's say they give you these two functions and then they ask you prove whether they are inverse to each other. So how we are going to do? Okay, so again we are going to apply back the composite function concept right over here, which we will find the fgx and gfx. and see whether they can get back the same answer, which is x. Because to this concept, we know that f inverse f, you get back x. And this itself is a composite function, if you realize, because it's combining more than one type of function. So the concept comes from here. F inverse fx, you get back your object, which is x. So here we can show it to the composite function as well. So if both of them lead to the same answer, you can expect that they are inverse to each other. And so you should get back the object of the function when inverse function pairs back to the normal function. So that's how we can see. So let's try out fgx and gfx of this function. So let's say I want to start with fgx first. So you have to sub gx first according to the order of the composite function. So this becomes your object for your f function, which is x here. So you'll sub this inside x. So it will be 3 minus 2, 3 minus x over 2. So you will get 3 minus bracket 3 minus x. So when you expand, you get x. But this does not tell any conclusion yet, because only one type of composite function gives you back the same object of x. So you have to try with another possibility of g of x. So g fx is 3 minus 2x. So this comes your object for the g function. So you sub this inside the x. And then you solve. You get 2x over 2, which is x also. So this proves that fgx is gfx, and both of them are equal to x also. So although they didn't write g as f inverse or f as g inverse, you should understand, although they put different alphabets, that these two functions are inverse to each other. That's how they can lead to a common composite function of x. So this is the concept behind it. So they can put any label they like, but this can prove that both of them are inverse to each other. And also we realize these two functions are linear equation, and linear equation has a tendency that can get to an inverse function through horizontal line tests. You see, one point of intersection only, one object, one image, one-to-one relation. So definitely one-to-one relation has inverse function because of this arrow diagram here. See, you can have two-way traffic going on here. So this proves it. And okay, so let's say I want to plot how the function of this looks, these two functions on top here. So let's say now we're going to draw a graph and see how does the inverse function look, so that you can have a better picture. So this might not be very accurate because I'm not doing a graph paper here, but let's see how it goes. So I'll put the y-axis here, x-axis here, 0. Okay, so the scale has to be uniform here. Okay, something like this. One more. Okay, so same for this side as well. Until negative, no negative. Okay, so we go down here. Okay, so 2 is your maximum value for both of these functions. 3 actually, for one more. Okay, so now the down part. So now we can plot and see how does these functions go about. So how we actually plot the graph is actually based on the table of values we construct. Means we sub random values of x or y to find the corresponding value actually. That's how we can construct the graph. Okay, so first let's say I take fx function. So 3 minus 2x. So I will draw a table out like this. You can try the values in your calculator. So I'll get a table like this. 0, 3, 1, 1, 2, negative 1, 3, negative 3, and 4, negative 5. So you can see here that, let's say I plot 0, 3, 1 here, and 1, 1. So 1, 1 will be somewhere here. 2, negative 1. 3, negative 3. Okay. And also 4, negative 5. Okay, so from here I can actually draw a shape already. It's supposed to be linear. Let me see whether it's all okay. Okay. So I will get something like this kind of graph. Not accurate, but almost there. So if, let's say I have a function 3 minus x over 2, I should get a table like this after I sub the values. 1, 2, 3, 4, 5. 0, 3. This is 3 over 2. 1, 3, and 5. Each column has none. So you will get 1, 1, 0, and negative 1. So if I plot, you have to plot it on the same graph, then only we can see the relationship happening. So 0, 3 over 2, 1 and 1. You see it has the same coordinate here. These two graphs share the same coordinate. 3 and 0. Can you see here? Here is 0, 3. But on this graph, it comes 3, 0. So you can see the inverse happening already. And then 5, negative 1. Here. Intersect here. Okay, so we have 4 points. So you see if I draw a line like this, can you see? These two graphs create an X sign here. So you can see something like this. It's like overlap to each other. So that's why they say it's inverse. Means it's already reflected on another side. So this is how you can see the inverse function to this graph. Whenever it forms an X symbol, you can already see that they're opposite to each other. One is going this way, another one has a negative gradient. So yeah. So this is the way you can see also. So now we're going to the application already, which is the last part. So application of inverse function. Okay, so let's say I have a question like this. So one person wants to build spherical balls that can hold 1/4 cm cube of water. So they give you this info here. And the question already told you volume of sphere V is given by V equals 4/3 pi r cube. So this one is something you should know by now already, but the question already gave you. So just accept it. So where r is the radius of the sphere. So now she wants to know how to determine R if V is given. So from here you can see a function happening which R is the object and V is your image. Means with a radius only you can get a volume of an object because it revolves around the object to form a 3D shape like a sphere. So first question is, they want you to draw an arrow diagram of the function f. So they gave you the label of the function as f, then maps R to V. And its inverse function as well. So inverse function will reverse the direction of a normal function. Means the inverse function f inverse will map V to R. Means you have your V, you're going to find R as your question. So the diagram will look something like this. So R will be here because it's your object, V is your image. So the normal function will go like this way, f. And you want to find inverse, you'll go the opposite direction, f inverse. So the function here will represent the volume, which is 4/3 pi r cube. So this is your arrow diagram done. So that's the first part of the question. And then the second part, they ask you determine the radius of the ball that can hold the above volume. So this is nothing much actually. It's just testing you, can you identify which is your object and your image based on this arrow diagram. That's why we create this question to proceed with this. So it's always interlinked. So from here, we can take the info 1/4 as B. B is 1/4. So 1/4 will equal to 4/3 pi r cube because this is the formula of the sphere. And this volume occupies the volume of the sphere. So we can find the radius, means it has to fill fully, or else we won't know the exact volume of the sphere. So how we're going to find R is, we shift the 4/3 pi here, you will get 3/16 pi equals to R cube. So R will equal to cube root of 3/16 pi. And when you press your calculator, you will find R as 0.84 cm done. So that's your answer for this question. So actually very simple only. They just make it sound complex through all this statement, but actually they're testing you on how can you identify your object and image and apply the inverse function here as well to get the radius from the volume. So yeah, so that's basically chapter 1 done already. So I'll give a summary for the chapter before we end. So summary is something very short that can show everything here, all the 3 subtopics already. And the next video will already be on trial papers question discussion. So you can see the pattern from there better. So summary of chapter 1. So in chapter 1, we know its function. So let me start from the middle. So this is a good summary that can help. So first of all, we learned about representation of function. And representation of function can actually involve arrow diagram and can also involve graph. If you want to break it down further, you can say it can also involve the ordered pair and the general equation as well. But these two are the main things tested, arrow diagram and graph. And we also learn a thing called function notation here. So how do we write function notation? So there's a specific way to write it. So f(x), f:(x) will map to 2x. If it's in an equation form, you write f(x) equals to 2x. So from here, we can identify that x is object 2x is image. So knowing object and image is the key to the success of you in this chapter, because the whole concept revolves around identifying the object and image first. Then only you can proceed with the further steps. And also functions, we told earlier that it can involve discrete or continuous function. And discrete you can learn later on, your discrete random variable which is shown in your binomial distribution, and continuous random variable which is shown in your normal distribution. So that's a good example which you can see later on. And from there onwards, we proceeded to composite functions and inverse function. So after that, you can see that composite functions, I can give you a circle to show it. So let's say I got 3 small circles here. So we have x, fx, and also gfx. So how we label the function here is x to fx surely is mapped by function f, and fx to get gfx, you're definitely going to map function g, and the total mapping, which is the composite function, is gf. So that's one type. Another type, another possibility, let's say here is x, here is gx, here is fgx. So from here to here, g function maps x to gx, and from here to here, f function maps gx to fgx. And then the total composite function is fg. So that's your composite function summarized. So basically your gfx is equal to g bracket fx. So this is how you should show in the exam. Same with fgx is equal to f bracket gx. And then inverse function we can show also to an arrow diagram. So let's say I got 2 circles here, and we have x and y. So f will map x to y, and f inverse will map y to x. So the relationship is something like this. These 3 key things you can understand from here. Fx is y, f inverse y is x, y is fx. And then the last thing, properties of inverse function, right here. So properties, how do we identify? So it's only restricted to one-to-one function, which has inverse function. Other relations will not have inverse function. And then another property, fgx is gfx is x. Means g and f are inverse to each other. And another property, the f inverse graph is reflection of f in the line y equals x. And the last condition over here, if AB lies on F, then BA lies on F inverse. So yeah, this is the whole summary of the whole chapter over here. So this is the whole thing over here. So I would like to conclude this presentation. So hope you like the video, and yeah, thank you.